Hi, I'm Łukasz, and this is the first video in a series about an active disturbance rejection control. We'll talk about the general idea behind ADRC and develop its building blocks. My goal is to arm you with the intuition and knowledge that will help you with further exploration and practical implementation of ADRC. I hope you enjoy it, and if you do, please consider subscribing so you won't miss the next videos. The knowledge I provide here is free, but if you want to support me, you can buy me a coffee. The link is in the description below. First, let's talk about the general idea behind ADRC and the first of its building blocks, the extended state observer. I assume you have a basic knowledge of linear systems, full state feedback, and the Luenberger observer. Video is quite dense with equations and diagrams, so I encourage you to pause and rewind if you feel the need. Let's get started. If you know anything about industrial controller, you know that the king is only one, the PID. It needs no model, no fancy math, and there are numerous ways to tune it. But what if the PID is not good enough for the job at hand? The control theory textbooks say that you can design an observer to estimate the state of the system and a controller to track the reference. But there is one catch. You have to model the system. Model can be linear or nonlinear, but you need it. What if modeling is impractical, expensive, impossible? This is where active disturbance rejection control comes in. It is a control strategy that does not require a model of the system. Instead, it assumes that the system is a cascaded integrator with a disturbance. The unmodeled dynamics and disturbances are lumped into a single term, which is estimated together with the state and used to cancel out the actual disturbance. Note that the order of the system is assumed. You can know it from the first principles, you can eyeball it from the step response, or just guess it and see if it works in practice. In this series, we'll use second-order systems as examples. They are common in practice, think of mechanical systems or DC-DC converters, and once you get the idea, you can easily extend it to higher orders. So, how do we estimate the state and the disturbance? Let's use a simple example of an actuated pendulum with an external disturbance. For brevity, I will omit noting of t for the input u, state variables, their derivatives and estimates. Zeta of t is the external disturbance, also known as an exogenous disturbance. Exogenous is a $10 word for something that comes from outside. The term with sign of theta doesn't fit the assumed model of a cascaded integrator. Therefore, we'll name it an endogenous disturbance. Yes, you get it, endogenous means that it comes from inside the system. Now we lump all disturbances into a single term, psi of t. We'll call it the total disturbance. Let's replace theta with a more general state variable x and rewrite the second-order differential equation as a system of first-order equations. Let's now estimate the state of the system. In general, a state observer for ADRC can be nonlinear. However, coming up with a nonlinear observer might be pretty hard, so in practice, we usually use a linear one. The observer's equations consist of two parts, prediction and correction. Prediction is based on the model of the system, and correction is based on the measurements. Our model has one output which is equal to the first state variable, but we need to estimate it nonetheless. Otherwise, what would we put in the correction part? Lambda 1 and lambda 2 are non-negative gains. Now, if you look closely, you will notice that the model is not complete. It lacks the term for the total disturbance. Let's add a new variable z. So, how do we estimate the disturbance? We'll use the same idea as for the state, prediction and correction. We don't assume any model for the disturbance, so there is no prediction part, only correction. This is the extended state observer. Now we have the estimates of the state and the total disturbance. Let's see how it works in the simulation. Okay, so for the simulation I will use the Julia programming language, Pluto.jl, for the notebooks with some custom styling, as you can see here, modeling toolkit, which allows me to write the equations in a pretty natural way, together with the differential equations for simulating them. So let's start with the pendulum model. There are two parameters, G and L, and we have our variables, state variables theta and omega, which are the angular position and velocity, u for the input, zeta, which is the external disturbance, and psi for the total disturbance. In the equation sections, the capital D, it means the time derivative, and this means equals, so we of course have d theta, which is equal to omega, and d omega, which is input u, plus the total disturbance, which consists of our unmodeled dynamics, so the endogenous part, and the external disturbance zeta, which here is some arbitrary function of time. I was also not very original with the input function, which is here just sine of t. So let's instantiate our pendulum alone and simulate it to see if it works as expected. So if we solve our ODE, we get and plot the variables, we get the position, velocity, and total disturbance here. So now we want to build the observer for estimating those values. So there are three parameters, which are of course gains of our correction terms. There are variables, so the estimates of the state variables, estimated position and velocity, and of course z, which is the estimated total disturbance. We have, and the observer, to be able to estimate those values, it needs the input and output from the observed system, so that's why we have the actual theta and control input u here. So those equations that you can see here, those are the same equations as I just showed you in the presentation, just instead of x1 and x2 we have the theta and omega. So there is no point in simulating the observer alone. We'll just combine it with the pendulum system and see how it works. So we instantiate pendulum and extended observer, and of course connect them. I think it's pretty obvious how they connect here. And here we can see the combined equations with the variables that are properly namespaced with P or O for the pendulum and observer respectively. So we'll do the same thing for the simulation. We'll solve our ODE for 0 to 10 seconds time span and see if we can actually estimate the state variables and the total disturbance. So for the angular position, you can see that it tracks perfectly, at least judging from this plot. Same goes for the angular velocity, but those two are not the most interesting ones. The most interesting question is, can we actually track the total disturbance? And when we plot the actual total disturbance and its estimate, we can see that yes, it does estimate it. We can track it with some lag, which is expected, as this is especially visible when the total disturbance changes faster. But there is, so yay, hooray, it works. But there is one more thing that I would like to show you, that of course gains are important, because if I overdo it, so I want even better, but it just exploded. But also if I make it too small, here you can see that it still tracks, but there is a significant lag this time. So as I said, in one of the next videos I will show you how to actually calculate them. For now I just brute forced those values to make it somehow work properly. And yeah, now we can go and use the estimated total disturbance to control our system. Let's now talk how to control the system utilizing signals from the observer. Our goal is to control the system in such a way that the output Y follows the reference signal R. The output Y is the first state variable x1. We also have the estimate of the second state variable x2, so we can use it to establish a full state feedback controller. But what is the reference signal for x2? Since x2 is the derivative of x1, we can use the derivative of the reference signal R. Let's write the control law for the system. Once again, controller can be nonlinear, but we will use a linear one for simplicity. As you can see, it is the constant gain PD controller that uses the error between the reference signal and the state estimate. But what about disturbance rejection? Let's take a look at the assumed system model. You may notice that the total disturbance Xi adds to the control input U. What if I could subtract the disturbance from the controller output? That would cancel the disturbance, leaving only the controller input. In reality, we don't know the disturbance, but as we have already shown, it can be estimated using the extended state observer. Let's then replace the disturbance with its estimate Z. Z tracks the disturbance, so we can say that it is equal to the disturbance plus estimation error epsilon of t. Now we can see that the disturbance has been reduced to a, hopefully, small estimation error. This is the essence of active disturbance rejection control. Let's then update the control law to include subtracting the disturbance estimate. Okay, let's admit it. There is an elephant in the room. How do we know the derivative of the reference signal? We'll address this issue in the next part, but before that, let's assume that we have it and see how the controller performs in the simulation. Okay, let's check how the controller works. We have the similar setup as before with the pendulum, this time without defined input signal, we have just the input U here. We have the extended observer, as we saw before, and we have a controller, which implements actually the same equation as we saw in the video, just with the state variables that are named here theta and omega. And as you can see, there are two gains, proportional and derivative. I just made them some arbitrary numbers for the sake of this example. We'll talk about properly calculating them later on. Okay, so let's wire them together. We have pendulum, we have extended observer, we have controller, and we have two additional signals. We have the reference tracking error, which is just the reference minus the actual angular position, and we have the integrated square error, which is useful for comparing different versions of the controller and comparing their performance. Our reference is once again simple sine of t, and it's easy to know what the reference signal derivative should be because it's just the cosine of t. And the rest is just wiring of the signals together. I think that's pretty obvious. So here we have the combined differential equations for our system, and once again we'll simulate from 0 to 10 seconds and see how it works. So let's jump straight into it. We have the actual position and the reference signal, and as you can see, it looks that it tracks pretty well. And we can also check the integrated square error, and you can see that it jumps in the beginning because estimator needs to catch up, and then it rises pretty slowly, which indicates a good performance. So just check if we can still track the total disturbance, and it looks that we do. And let's also take a look at the control signal, because it might be, jumpy or too big, but here it looks very reasonable and smooth. Of course, now there is a question whether subtracting the estimate of the total disturbance, so this term here, does it actually help? And of course we can here easily check it. So let's comment out this term and run the simulation again and see what happens. And if we take a look at the plots, we very clearly can see that the performance got significantly worse, and this tracking error is very clearly visible here, and we can also see on the integrated square error that is like 20 times bigger than it used to be. So it means that the secret sauce of the ADRC actually works. We left the last part with the elephant in the room. We need the derivative of the reference, but it would be too optimistic to assume that we would always have one already available. Maybe the reference comes from an operator turning a knob, not from a fancy planning algorithm. We need a way to calculate the derivative of a signal. Let's see how we can do that. Those of you who live on the complex plane would instantly say, just multiply by s. When we look at the frequency response of this system, we can see that the gain rises with frequency all the way to infinity. What does that mean in the time domain, and how do we implement it? Well, such a system would require the ability to start its response before the input signal changes. In other words, it would need to predict the future. We call it a non-causal system. Implementing such a system might be a little hard, unless you have access to some special resources. So how can we transform it into a causal system? Quite simply, we need to stop the gain from rising with frequency at some point. We can achieve this by introducing a pole into the system. Let's see what the frequency response of the system looks like. The gain rises with frequency, but only up to a certain point, which makes it a causal system. If it looks to you like a high-pass filter, you're right. However, we use it differently here. Typically, with the filter, we are interested in signals above the cutoff frequency. Differentiation, on the other hand, happens only below this frequency. Above it, we have high-frequency noise, which gets amplified and can wreak havoc in the controller. Before we try to solve that, let's see what the system looks like in the state space. It's a simple first-order system. Our goal is to decrease the gain at high frequencies so that we don't amplify the noise as much. How? Yes, you guessed it. We need to introduce another pole into the system. What it does is make the gain drop with frequency at a certain point. As before, differentiation happens only below the first cutoff frequency. But now we have a second cutoff frequency, above which noise starts to be damped. This makes the system more robust against high-frequency noise. This is how we arrive at the tracking differentiator, which aims to track the derivative of the reference signal without amplifying high-frequency noise too much. This was the last missing piece of the puzzle. Now we have all the building blocks to create a full active disturbance rejection controller. Before we conclude, let's return to our simulation and see if the tracking differentiator really does its job and how the full setup performs. Okay, let's now see how the differentiators actually work. I will first create the simple differentiator with just one time constant. As you remember, it's a simple first order system, and I made the t to be 0.1 second because I assume that my reference will be pretty slow. And for the tracking differentiator, there are two time constant. You can see that this actually the t2 is is the value that corresponds to the t from the simple differentiator, and I just made the t1 to be 10 times smaller. And here you can see that we have two state variables, as this is the second order system, as you remember. And I created a simple test bench for both of them, so tracking and simple differentiator. Only one addition is that because I added some artificial noise to my reference, I also created a signal that is, let's say, clean version of that reference that we can use for comparison. And as you can see, I feed both tracking and simple differentiator with that value, and let's check what are the outputs. So after we simulated as usual for 10 seconds, we can see, and okay, one more thing, I had to tighten the tolerances here a little bit because of all of that high frequency noise. And you can see that with the simple differentiator, yes, it tracks the reference with some delay, but there is quite a bit of high frequency noise there. While with the tracking differentiator, we can also observe the delay, and we can also observe that it needs some time to catch up, but the noise is way less visible than in case of the simple differentiator, and that's the whole promise of the tracking differentiator, that is more robust to the high frequency noise in the input signal. So now there is one more step to do, is to take the tracking differentiator, put it in the whole setup, and see how it works now. And once again, we have pendulum, extended observer, controller, and now tracking differentiator. And only change in the controlled pendulum system is that now, instead of saying that r dot, so derivative of the reference, is the just cosine of t, we say that it's the output of the tracking differentiator, and we of course feed the input of the tracking differentiator with the reference signal. So now let's see how does it still work and how it works. And when we check the simulation outputs, we can see that we are still quite good, but worse, which is clearly visible on this plot, which looks the same as before, but if you check the scale, the integrated error is like 3 times bigger than it was in case when we knew exactly the derivative of reference, which is, I think, expected because we saw some delay in the tracking of the derivative in case of TD alone. But it's still pretty well. Of course, we can spend some time on tuning the tracking differentiator as well, but as we'll see in the next videos, maybe we don't need it at all. Let's do a quick recap. We assumed the system is an input disturb cascaded integrator. We lumped the unmodeled dynamics and disturbances into xi of t. We designed an extended state observer to estimate the state and disturbance. We used a simple PD controller to establish full state feedback. We subtracted the estimated disturbance from the controller output to cancel out the actual disturbance. Finally, we implemented the tracking differentiator to calculate the derivative of the reference signal and validated the entire control scheme. In the next video, we'll explore whether we really need the reference signal derivative and the tracking differentiator. This will lead us to the error-based ADRC. We will also see how we can properly calculate the gains for the observer and the controller instead of guessing them. All of this will provide us with tools to design a practical control system. Thanks for watching and see you in the next video.